In this lecture, I'd like to present interaction of beam and column doing second order analysis. That means nonlinear analysis. Okay, let's look at this one. You see the column here and the beam here. At the top of the column, we have the axial force P. On the beam, we have uniform load omega. The beam length L, the stiffness is EI, column L, and EI, A, B, C. You know how to do first order analysis of this case because you have already learned in your undergraduate course, right? So if you do first order analysis of this frame, then is this one. That is the result of first order analysis. MPC equal omega L square over 16. The maximum moment at the beam equal 49 over 512 omega L square. The maximum moment location equal 0.562 L from here. And the maximum moment at the column is at the top, right? So this maximum moment and maximum moment location depend on beam and column interaction, right? So if you have different EI in column, you have the different result, maximum moment and this location also. We ignore second order effect in first order analysis. Now from now on, let's do second order analysis. That means P, small delta effect, consider. As you see, it is the braced frame, right? There is no lateral displacement due to right hand side of the beam is hinged, right? No lateral displacement. So we only have P small delta effect due to member curvature, okay? Member deflection. P small delta effect should be considered. So in the second order analysis, maximum moment and location depend on interaction of beam column, the same as the first order analysis, and also the magnitude of P. This P increase, maximum moment, location change as P increase because we are doing second order analysis. I'll show you process. So this second order analysis, the axial force in the beam is neglected. A little axial force may occur if we do second order analysis. The axial force at the beam ignored. And second assumption is that axial force in the column is function of P, not function of P and W. It means the column axial force only consider P, not W, for making the problem simple. Otherwise, it will be much more complicated. From now on, let's do second order analysis of column first. Let's look at this. Let's assume the moment at B direction is MBA. That is MBA. That is MBC because this is C. MBC. We consider the same direction because we will use the slope deflection equation later on. So we assume the clockwise moment. If we have the moment here, MBA, we have the reaction here, MBA of L, right? Lateral reaction due to this moment. And then we take out this part. That means we make a free body diagram for column analysis. Then P, reaction, P applied, lateral load, MBA over L, and M internal moment, M internal equal minus EI Y2 prime. That is the column coordinate. So YC 2 prime. EI YC 2 prime. M internal moment equal minus EI YC. This direction. YC 2 prime. That column, that deformation. If we have some large P, then column moment developed like that. If we consider second order effect like that, that the maximum moment location is called XC, and then maximum moment MC maximum. From this one, we can establish the equilibrium equation, M internal minus PYC, right? Minus, due to this lateral load, MBA over L XC equals 0, internal minus EI Y2 prime, and then divided by minus EI, then we can get this equation. K square is P over EI, right? for this second order differential equation, then we can get the general solution like that. Yc equal a sine kx plus b cosine kx minus the homogeneous solution and particular solution, MBA LEI k square xc. So in order to get a and b, we need two boundary conditions. At the bottom of this column, so displacement equals 0. Right? So yc 0, 0, cosine 0, 1, b, 0, b equal 0, right? YCL, here displacement also 0. YCL. From this equation, you can get A equal MBA P sine KL. So ultimately, YC equal, you have this term and this term. Okay? So you can arrange in this equation. YC equation. So from this YC, displacement equation of the column, right? From this displacement, you can get maximum moment. How to get? Firstly, you have to get the YC prime, right? That is slope. From this equation, can you calculate YC prime? Yes. Let's look at the shear force first. Shear force equal minus EI YC 3 prime, right? Yeah, so 1 prime, 2 prime, 3 prime. Then you can get this equation from here. For maximum moment location, shear force must be 0. From this condition, you can get the location. Then must be 0. So from that equation, cosine kxc must be 0 because MBA is not 0, k is not 0. So cosine kxc must be 0. So kxc equal pi over 2. So now you find out the maximum moment location. Then how to calculate maximum moment equation? MC equal minus EI y 2 prime, 1 prime, 2 prime. That is equation number 1. If you input this one into here, what happened? Kxc pi over 2, sine pi over 2. What is that? 1. So MC maximum equal MBA divided by sine KL. Okay, that is MC maximum. What is that? MC maximum. We obtain through second order analysis, geometric nonlinear analysis. So you get MC maximum, and then we have to calculate MC maximum, that the beam moment maximum, and then this end moment, right? Or let's calculate one by one. Let's look at the beam analysis. Beam, right hand side is hinge, so moment 0. So left hand side is MBC. We call it MBC moment. So from this one, you can calculate the shear force, right? Omega L over 2, right? Due to this moment, MBC over L minus, right? Through the equilibrium equation, you can calculate this shear force. And let's consider this kind of the moment shape. XB is MB maximum. Okay, maximum moment location is XB. It is called XB, maximum moment location. So as our assumption, we ignore the actual force on the beam, right? So there is no actual force. So the result is the same as our first order analysis, right? Yeah. So we can get simply the maximum moment without using any differential equation. Okay, let's look at this one. So the maximum moment location is VB minus somewhere here, let's say XB omega XB. That is the shear force must be 0. So from this equation, maximum moment location XB equals this one. So MB maximum moment here is a moment at this location. How to calculate the moment? MBC at B, MBC and VB times XB minus omega XB square over 2, right? Yeah, like that. So if you rearrange this equation, is this one. As you see, MB maximum is a function of MBC. How about MC is a function of MBA? So we have to know MBA and MBC. Let's calculate MBA and MBC. Yeah, MBC is this one. MBA is this one against the column. So MBA, MBC using joint compatibility and equilibrium, we can calculate MBA and MBC. So we need two equations. MBA, MBC. One is joint compatibility. One is from equilibrium. We have two unknown. We have two equations. Finally, we can solve it. Let's look at the slope deflection equation. MBC against the beam. MBC means this one. Because there is no actual force, we can write slope deflection equation as this. Simple form. EI over L 4 theta B plus 2 theta C fixed end moment. Okay, minus omega L square over 12. Yeah, counterclockwise fixed end moment. Yeah, so like that. MCB equal EI over L, so E theta B 4 theta C omega L square over 12 is clockwise, so plus fixed end moment. Yeah, so MCB moment at here equal 0. Why? It is hinge, so it is 0. From this one you can get the equation theta C of this, right? So the MBC, you can write MBC equal, if you input this equation here, you can write MBC is a function of only theta B, but not theta C. From this one, theta B can be written as a function of MBC. So you have the angle from beam. Then let's have the angle from column. From column, you have the equation here, y prime. That is the column angle. YC prime equal, that is the angle, okay, from the column. As you know, this theta and this angle must be identical. This one from the beam, this one from the column. That angle must be identical because it is the rigid frame. The connection angle remain 90 degree. Before applying the load, the connection angle is 90 degree. After loading, the connection remain 90 degree. Connection angle. So theta B and this column angle must be identical. But this one is, as you see, this angle is minus x plus y. So minus x plus y. That means sign is minus. Originally minus sign. If you make the plus sign, you have to add minus here. Then it is plus. Then we can make equal to theta B. So this is apply the minus here, okay, is equal to this one. Minus this equation equal to this one. From this equation, we have one equation as a function of MBC and MBA. You have two unknown here, MBC and MBA. So you need one more equation. You can use equilibrium equation, joint equilibrium. If you see, that is MBA, that is MBC. The joint moment, the summation of this joint moment must be 0. Why 0? If it is not 0, what happened? The joint must be rotate in order to get the equilibrium position. In order to satisfy the equilibrium, the summation of this joint moment must be 0. So it is equation. MBA plus MBC must be 0. Yeah, equilibrium equation. So you have two equations. This equation 1, this equation 2. You can solve the unknown MBA, MBC. If you solve these two equations, MBA equal minus MBC. If you see this equation, minus MBC equal this one. If you solve these two simultaneous equations, you can get this equation. Do you understand? Now you finally got the maximum beam moment equation, maximum column moment equation, and MBA, MBC. You got the moment equation now. As you see here, moment is a function of omega. Of course, omega. Function of, again, what? K, right? What is K? K square equal P over EI. That means your moment is a function of P. If P change it, resulting moment must be changed. That is the result. If P equals 0, that must be the same as the result of first order moment. First order analysis, right? MBC omega square over 16, like that. You have already seen this result, right? Okay, if P increase, but P must be less than PE. In this range, the maximum moment occur like that, within at the column, like that. And then the maximum moment location at the column must be greater than 0.5 L, above the mid height, somewhere here. And then XC, the maximum moment location within the beam must be greater than 0.5 L. Okay, like that. If P equal PE, this apply load, P equal to PE. In that case, it is a very specific case. MBA, MBC equals 0. 0, 0. So pin and beam. So maximum moment equal omega L square over 8. Very long value. Because MBA, MBC equal 0 means it behave like the hinge under P equal PE. So simply supported beam. So maximum moment, the same as the simply supported beam. In that case, if we calculate M maximum column through the previous column equation we already derived, then we get this equation. So maximum moment location is 0.5 well at the beam. At the column also mid height, right? If P equal greater than PE, then like that. This moment is plus moment. If you see here, minus moment here, but if P equal greater than PE, moment plus moment like that. Somewhere here. Maximum moment location, XB equal less than 0.5 where some left hand side move. Maximum moment as you see must be greater than this one, omega square of 8. And then moment diagram must be like that. So maximum moment location at the column less than mid height, right? XB equal XC equal less than mid height when P greater than PE. If you see here, if you see this case, if there is no column here, that means hinged one. Let's consider hinged beam, hinged simply supported beam. In that case, the maximum moment equal omega L square over 8. But column exists here, the maximum moment at the beam reduced due to this column. So that means column helps beam, okay? Column less than beam when P equals 0. When P equals PE, this point looks like the hinge, so there is no interaction between beam and column. So if P greater than PE, then beam moment become bigger than omega square over 8. It means this column cause to increase beam moment. So this column makes beam moment bigger. So in the case, this beam helps column. Beam helps column because as P increase, this column become weak. So this beam helps column. This beam less than column. Due to this column, beam moment increase. That is very interesting phenomenon due to as P change. Up to here, this column helps beam. So we can draw this. This is the column moment, beam moment, divided by omega L square over 8. Omega L square over 8. Omega L square over 8 means maximum moment at pin and column. Let's look at this one. P equal PE. That means maximum moment of the beam is omega square over 8. Let's look at this one. P over PE. P equal PE. P over PE is 1.0 in this point. Beam maximum moment is what? 1. 1 means this value is 1. So maximum moment is omega square over 8. You can see this curve like this way. If P equals 0, the maximum moment is this one. Why? Beam maximum moment is this one. And then column maximum moment is this one. P equals 0, beam maximum moment is this one. Column maximum moment is this one. Minus 0.5, right? Yeah. Omega square of 16. That is just 0.5 times of this one. Minus. Because we divide by omega square of 8. 0.5, 8, like that. MBC curve, also same, like that. Beam maximum here, maximum moment equal this one, M maximum equal MBC, MBA, the same. So as P increase, MB maximum increase like that. MB maximum increase as P increase. MBC also firstly minus and 0 and plus. MBC, this one, minus, 0, plus. Like change like that. MC maximum, minus, this value, create. Like bigger and bigger, like that, minus moment. Okay, that is graph. So that is the exact analysis. If we use AISC, the equation, K factor, maybe you learn this K factor calculation from undergraduate study, and also you will learn later on. If you calculate the K factor, effective length factor, equal 0.839, you will learn how to calculate this one exactly. Then you have a very close value like that, AIS curve, compared to the exact values. If we assume the K factor of this column equal 1.0, then it overestimates the moment. So finding, when P equal less than PE, beam cause the column the moment. So column helps beam. When P is greater than PE, column cause beam moment. Beam helps column. When P equal PE, shows the simple beam behavior. So AISC with K equal 1 overestimate the column moment. ISC with K 0.839 gives an excellent correlation. That is maximum moment location. That is column maximum moment location. If P has the small value, the column at the top column moment is maximum, right? If P increase, the maximum moment location going down and down. Beam case, the maximum moment location slightly change like that. Okay, finding. So when P is less than PE, XB, maximum moment location on the beam is greater than 0.5 L. Maximum moment location, column greater than 0.5 L. When P or PE, XB, when P greater than PE, XB is less than 0.5 L. XC equal less than 0.5 L. When P equal PE, XB, maximum moment location, XB and XC equal 0.5 L. You already see this figure. See you in next lecture. Okay, bye everybody.